My sincerest greetings to you all. Welcome to the Ephemeris Podcast, an astronomy podcast, where we are in season 2 talking about cosmology and things of the sort. I'm your host, Aphelion. Thank you for joining me on this episode today. If you are a regular viewer of the channel, you will know this is not my regular uploading schedule. I'm not one to upload on a Monday, and the main reason for that is just because the research of this episode took way longer than I expected, and I actually really wanted to get this one out on Sunday, but it just turns out that I had quite a few writing pieces from our subject today who or the writing pieces were really long, basically. So yeah. Anyways, that just means that you guys get a longer episode. So without further ado, let's just get into it. Today's episode is on Arthur Eddington, and I was thinking about covering Russell, but some of his stuff meshes here, so I think we can just skip to Eddington. So Arthur Eddington was very influential to our understanding of stellar evolution, especially when we consider the mass luminosity relation and the Eddington limit. So let's get into his biographical details, because that's how we start off every episode. Eddington was born in December of 1882 in Westmoreland, England, and he was the son of Quaker parents. However, his dad did pass away quite early when he was 2, so he was raised by a single mother. He was academically excellent. He earned a scholarship to the University of Manchester, it was Owen's College at the time, but I digress. He was admitted at the age of 16, and that's really weird to think about, because if I was in his position at this time in my life, I would be a sophomore in college. So yeah, very, very odd. Eddington turned towards physics while he was studying, and he performed so excellently that he transferred to Trinity College, Cambridge, on a scholarship. So that's another scholarship. Not only did he get into one college with a scholarship, but then he got into Cambridge with a scholarship. And so even after that, he became the first ever second-year student to be placed as a senior wrangler and secured a position at the Royal Observatory in Greenwich. So yeah, that's a really, really nice position to be in very, very early on in your college career. And so we can now begin discussing the work of Eddington. So after Eddington secured his position at the observatory, he did regular observational work, but then he started writing some essays on proper motions of stars in like 1907, and I think at least one of the ones that I'll discuss today was a award-winning one. So some of the ideas that come out in his essays are very interesting. I'm just gonna go over them really quickly, or not quickly, depending on how long you think these explanations are going to be. So, the first quote that I've gathered here is, if the whole universe forms one system, or one chaos, we can speak of its motion relative to the sun, but it is more natural, though perhaps misleading, to speak of the sun's motion relative to it. Now that's very interesting. This sets up some ideas about drifts of stars and sort of like star streams. But also, we can just take this quote right out of the writing and think about how it tells us that science at the time is moving away from the idea that the solar system isn't the only solar system, and the perspective is shifting about the universe's motion away from, the solar system. And that's pretty crucial, because otherwise our understanding of the universe stagnates. We can't really get into, relativity and Doppler's principle and Hubble's law if we are not very familiar with the idea that the solar system isn't the center of our universe. So yeah, as I mentioned, he goes on to explain drifts of stars, and he defines it as haphazard velocities of a system of stars relative to two axes, which is caused by the star's motion relative to the system. When he comes back to the ideas that he mentions in this definition, he realized that, axes are arbitrary, but that's just the way that he's put it here. But let's just hold on for a second because this definition is actually a bit complex. So, haphazard velocities, what does that even mean? Let's picture it this way. If you observe someone throwing a tennis racket up and away from themselves, right, from the side. Let's imagine we're at the side of this person throwing this tennis racket up and away. The trajectory of the handle of the tennis racket, if you look solely at the handle, would not be a perfect parabola. That's because the handle is moving relative to its system, which is rotating. So if it was just like, there's absolutely no rotation, yeah, maybe it would be a parabola. Now, imagine the handle of the racket is a star, and the other end of the racket is another star in, I don't know, say, out in space. And they're a binary system, just traveling however they're traveling. So what Eddington is getting at here is that the motion, if you see it from one star, becomes haphazard because it's not just like, going straight this way, straight that way, straight one arbitrary axis. It's doing sort of a drift of a star, and he's going to talk about how it's caused by two significant star streams. I don't know how relevant that idea is now, but it's definitely an idea that was in his essays. So, yeah. Once he defined this, he experimented with the idea of a single drift, but then he realized that there must be two drifts. So, kind of two drift, two streams, kind of interchangeable terms here, I think. I'm not capable of explaining all of the mathematics that goes behind how he justified like two different star streams, but he used a bunch of tables, diagrams, equations, and derivations to figure it out, and I hope you can believe me on that. He did end up discovering a third drift. For the most part, he disregarded it though, so we're not gonna focus on that too much. And other than that, he found a mathematical proportion that applied to all observed distances in terms of drifts. And he inquired how that affects average distances between stars, but just, that is the fact of the matter. Lastly, Eddington concluded, and this is in, I think, a separate piece, that the magnitude of the proper motion of a star is inversely proportional to the distance of a star. In other writing about theories of star motion, Eddington contemplates two possible states of the universe, a single system universe and a two system universe. Because let's just be clear here for a second. Hubble hasn't come around and been like, hey, there are galaxies out there. Milky Way isn't the only one, right? So basically, Eddington, in his assumptions, is stuck in this idea that we have the Milky Way. It's got a bunch of stars. It's very big. So the distances of stars vary, but there's a possibility of two systems in the universe. But yeah, so going under that assumption, Eddington does state specifically, in fact, it is difficult to see how gravitation towards the center of the universe could separate the motions of the stars into two systems if they originally formed one system. And while this doesn't mean to imply there is no center of the universe, as I've explained with the context, there can be some implications about the universe with this statement, if you dig deep enough. And so, yeah, that is pretty much proper motion stuff that he did in 1907. It is quite a lot to digest, so I had to spend quite a lot of time figuring out how to explain it. So, after that, Eddington worked to explain a mechanism through which Cepheid variables were possible. That was another thing that he worked on, I think, in the 1910s. In doing so, he identified some key forces that he believed would keep stars stable, and among these were gas pressure, radiation pressure, and gravity. And he was the first to model the interior of a star under radiative equilibrium in this manner. He also realized perfect gas conditions were possible in stars because of the high ionization of internal gases. I'm not going to get too deep into the chemistry of this stuff, but just to know that all of the stuff that he is saying here will lead to a very good direction, because he extends um, Carl Schwarzschild's work. I can't pronounce that last name for my the life of me, but forgive me on that one. So his work on radiation pressure, and he went against method developed around classical mechanics. And I don't know if that sounds like a good thing or a bad thing, but classical mechanics aren't necessarily what happens in space. So yeah. Also, Eddington wrote Stellar Movements and the Structure of the Universe, and this is where there's a lot of notes. So buckle in. It's going to be a pretty huge work that we're going to delve into right here. In the Stellar Movements and the Structure of the Universe, Eddington investigates 6 characteristics in the first chapter of variable stars, novae, and binary systems. And he organized his findings based on the characteristics, so I will too, and we will just go down the list. So the first one is apparent position in the sky. I think there weren't like specific writing or whole paragraphs and essays about this characteristic, but it's very self-explanatory. The apparent position of a star would be important because imagine a protostar. It'd have to be in a star-forming region, obviously, or a molecular cloud or something of the sort. Otherwise, it would make absolutely no sense that a protostar is just out on its own, floating in the cosmos, right? So apparent position in the sky. Then there is magnitude. This is where it gets a little bit more interesting. In this section, Eddington utilizes apparent magnitude to conclude that the brighter the magnitude, the more light we receive from it. And now that is a very, very obvious statement, but you have to realize that he put a lot of math behind it and kind of put it all together using like logarithms and proportional constants, and deriving these proportional constants is really difficult. Eddington pretty much committed his life to it. He's like pretty much a man of constants. But yeah, anyways, that's how he brought some value to magnitude as a factor for the characteristics of stars. So the next factor is type of spectrum or color, and Eddington in the text says that these two things are interchangeable, but one is more convenient because type of spectrum directly tells you about color, whereas color does not do the same. So Eddington utilizes the Draper version of the Harvard system to explain the importance of the spectral type in identifying stages of stellar evolution and common characteristics. And he pretty much just goes on to say that as a star evolves, its spectrum changes in the types of lines and bands that it has and how intense they are. And so it starts with, a star having a complete spectrum, no lines, no bands. Then lines start to appear and bands start to dim or shorten in length. And in this process, stars go from having prominent hydrogen lines and bands to having a calcium spectrum to obtaining heavy metal lines like titanium oxide. And if you've ever done any sort of basic research on spectral classification, you'll know this holds very, very much true when we study these topics today. So really we can consider this to be the final piece that is needed for the Harvard classification system to become, as prominent as looking at an HR diagram to understand stellar evolution. And because, previously you could really say that the Harvard system didn't have any continuity. It was these stars have these spectral lines, so this is where they belong in this category. But there's no connection between those spectral types. They're just, this is what it is. And so when you take that a step further by saying, okay, well, stars have an evolution in spectra, so now we can show the connection, that becomes really, really important. So, yeah, the next factor is parallax, and Eddington gets a little nitty gritty with the details of the parallax of stars because, again, it is mathematics, and I myself have a lot of trouble, you know, breaking down mathematics that I barely understand. But there are some important takeaways, and those things are his application of the parsec, which was first defined by H.H. Turner, and the consideration of calculating the mean and absolute parallaxes of stars, which he gets into in some other chapters that we won't discuss, but it, in general, it was an important factor to cover. It's not like, a throwaway concept. He talks about proper motion. We already went over that in the last work, and I think these ideas of proper motion for him stay throughout his career and his writing. So it's not really necessary to get into what he wrote in for that factor. And then we have radial velocity. And so here is where Eddington applies Doppler principle for identifying the velocity of a star moving away from us in our line of sight using a spectroscope. And yeah, so those are some of the simplified factors that I've mentioned at the end. But yeah, in whatever, damn, I'm forgetting the name already. Where is it at? Yes, stellar movements and the structure of the universe. So in this work, after the first chapter, I know that was the first chapter. He does also mention the mass and density of stars and brings up some intriguing concepts. So, firstly, he equates the combined masses in a binary star system to the semi-major axis length cubed over period squared. And you can really imagine this as a rendition of Kepler's third law because, I mean, it's basically the same variables, just, change around kind of like the mass of Earth with some different stuff and sort of have the same g and pi constants in there. So, Eddington also creates an equation for the density of a star using its radius, luminosity, surface brightness, mass, and distance, which is pretty impressive. Because when he puts it all together in his equation, there are multiple powers that you have to worry about, multiple relationships. It's pretty crazy. And yeah, this only applies to binaries, which I think he prefaced in the beginning of the writing itself that, the chapter, or even really, yeah, pretty much the chapter. So, yeah, moving on. Eddington begins to explore some theory about the universe and comes across the idea of a matter that obscures stellar objects and makes them dimmer. And in the most technical sense, you can call that dark matter. You can consider that an explanation of it, but it's not the dark matter that we think of today. Today we think of just like dark matter that holds up galaxies and kind of fills in the gaps of the universe and allows for the expansion of the universe. So, another thing that Eddington also mentions is, quote, now it is found that there is a regular progression in the size of linear motions from the youngest to the oldest stars, unquote. And just for a moment, if we exit Eddington's perspective and think about it from a Big Bang Theory perspective, I'm just curious, would its components complement this argument? I wonder. So, another statement that Eddington made about the evolution of stars with the universe is, quote, in a primitive state, the star-forming material was scattered much as the stars are now. That is, densely along the galactic plane up to moderate distances and more thinly away from the plane and at great distances. Where the material was rich, large stars with which evolved slowly were formed. Where it was rare, small stars which developed rapidly. The former are our early type stars. Not having fallen in from any great distance, they move slowly and in the main parallel to the galactic plane. The latter, our late type stars, have been formed at a great distance and have acquired large velocities in falling in. Moreover, since they were not necessarily formed near the galactic plane, their motions are not predominantly parallel to it. So, yeah, this is very interesting because we get into this idea that, okay, so at the beginning of the universe, um, whenever it was, there were large stars near the center of its beginnings, which had a large mass, which allowed for less velocity and created, some momentum for those stars moving away in a, I think he assumes a 2D plane. He doesn't really go into three dimensions when he visualizes um, his model of the universe. But anyways, so you got these large stars, and then you got small stars, which are with low mass, high velocity, and they're moving away quicker. And this is kind of the way that he justifies sort of two different star streams and um, how stars are moving in their proper motion. So yeah, very interesting idea. And then in the third and fourth chapters, pretty much the content concerns the nearest stars and clusters of stars, which isn't the most important thing. But in chapter 5, Eddington goes back to the idea of a lack of reference space frames in space. So kind of like with the essays in 1907, his definition of axes or his inclusion of axes in the definition. This is kind of a point where he realizes some things about that inclusion. And so he says, quote, "In reality, the manner in which the observed motion is to be divided between the sun and the star is indeterminate. These bodies are moving in a space absolutely devoid of fixed reference marks, and the choice and definition of a framework of reference that shall be considered at rest is a matter of convention." So yeah, that's definitely something interesting for him to consider. Chapter 6 and 7 of this piece get into star streams. We've kind of already discussed that. And in chapter 8, Eddington gets into the relation between spectral type and linear speed. And that's where I'll wrap up this piece, because, I mean, we could get into a buttload of detail, but it's going to make this episode like 30 or even 40 minutes long. So, after stellar movements and the structure of the universe came the Great Eddington Experiment. And in this experiment of Sir Arthur Eddington, which he would become, he sought to affirm the theories of Einstein by traveling to Principe to observe a total eclipse and look for gravitational deflection. Gravitational deflection of starlight passing near the sun, which was predicted by Einstein. And I may get into more detail about this experiment if we discuss this part of Einstein's work, but for now, we'll let that explanation be. Pretty much what should be taken away from this episode specifically is that the publishing of these findings in the experiment is really what put Einstein on the map. Because obviously you can create a whole lot of theory, but you got to get it proven. And if you got an experiment where people find that it's true and there's like concrete evidence now, that is very, very important for the notoriety of scientists who create those theories. So yeah, the next of Eddington's feats is the discovery of the mass-luminosity relation, and essentially what it is an equation that compares the luminosity and the mass of a star to that of Earth to determine the distance to binary systems and the stage of a star's life cycle, among other things. There are multiple applications to it, but I think those are probably the most important ones. And yeah, I mean, that's a pretty concise definition. There are obviously complex derivations to look into there, but that is the gist of the relation. And lastly, Eddington correctly speculated that the source of fuel for stars was the fusion of hydrogen into helium. and liberating enormous energy according to Einstein's equation E equals to mc squared. And after the 1920s, which is where he did a lot of the Eddington experiment stuff and figuring out sort of star variability, he worked on a quote unquote fundamental theory which contained quantum theory, relativity, and gravitation. And I think he was also on the hunt for some other constants and other things about Eddington. The Eddington number and the Eddington limit. The Eddington number is the approximate amount of protons in the universe. He estimated it to be 1.57 times 10 to the 79th power, but it is now estimated to be closer to 10 to the power of 80, which means that is a large number. I don't remember if this number, the Eddington number, is bigger than the number of years it would take for a white dwarf to become a black dwarf, or whatever that was in the black dwarf episode. But anyways, I digress. The Eddington limit is the maximum luminosity a star can reach while remaining gravitationally stable, which kind of comes from the mass luminosity relation. So yeah, that is all I have to say on Sir Arthur Eddington. If you guys enjoyed listening to this podcast episode on him, I know it is very, very lengthy. I think it's actually coming on 30 minutes of runtime. First of all, thank you for actually sticking around. Average view duration is quite low, and if you are watching till the end of these episodes, I do actually sincerely appreciate it. And I do, as I say always, I do appreciate a subscribe on YouTube, a follow on Spotify. In terms of this week, I know I promised to cover some missed episodes this week. I'm working on the notes for the next few episodes. Hopefully I'll get at least 2 episodes within the week and then get one on Sunday, so that there will only be one missing episode for me to kind of cover up for. So yeah, that is all I have to say in this podcast episode. I will see you guys in the next episode, whenever that is. Later.